Okay, so part 4 then, the difference between intermolecular and interatomic forces. Now we're going to take a look at 3 characteristics. What are they? Are they bonds between atoms or molecules? What's the strength? And then also the distance between the atoms and the molecules. So interatomic forces, like we said, the bonds between atoms. In other words, taking something like, let's say, sodium chloride, normal table salt that we throw in our food. Interatomic forces allows atoms to bond to each other and gives them new properties. Chloride is poisonous to us. Sodium is poisonous to us. But when the two bond to form sodium chloride, we can put it in our food. It's not poisonous anymore. The molecule has its own characteristics. So, it is the force between atoms. It's an incredibly strong force. And then there's a very, very short distance between these two atoms actually bonding to each other. Intermolecular forces, on the other hand, is the forces between molecules. They are relatively weak compared to interatomic, and they have a much larger distance than, for instance, the bonds found in interatomic. Also, intermolecular forces, for instance, in a solid is stronger than in a liquid. We even do find intermolecular forces between gas particles. So, before we move on then, we're going to take a look at the following example, where they want us to tell them what type of intermolecular force would hold these together. Okay, so the first one, they say, what if we have a glass full of carbon tetrachloride? Okay, so we go and we take a look at the carbon tetrachloride molecule. So it's a carbon atom that's bonded to four chlorides, and we know that this molecule has that general formula AX4, which makes it a tetrahedral molecule. Okay, we also know that the shared electrons, because the electronegativity of chlorine is 3, carbon is 2.5. So in all cases, the shared electrons spend more time around the chlorine than it does around around the carbon atom, making the entire outside of this molecule slightly negative and making the central carbon atom slightly positive. Now, AX4, our tetrahedral molecule, is our ideal shape. So this then would be a non-polar molecule. Okay? Now, because it's a non-polar molecule, we know that we're going to be dealing with non-polar and non-polar. And when we have this situation where we need to figure out what type of intermolecular force are we dealing with, we can go back to that table in the beginning. We can say, okay, so we ask ourselves, are there ions involved? In this case, no, there is not. Are there polar molecules involved? And we say, no, there is not. It's a non-polar molecule bonded to a non-polar molecule. So in this case, we know that we're dealing with London forces, or induced dipole forces. Okay. If we then go on, they tell us sodium chloride in water. Now, what you need to remember is when we calculate our electronegativity differences, anything with a difference in electronegativity greater than 2.1 is ionic. And then we have that exception to the rule that if it's a group 1 and 2 element bonded to a group 7 element, it always forms ionic bond. So that means in this case, our sodium chloride is ionic. And because it's ionic, we know it's going to be forming ions, and we know the water molecule is polar. So again, we can go and we can say, right, are there ions involved? Yes, there is. The sodium chloride forms ions. Are there polar molecules and ions present? Yes, because we have the sodium chloride that forms ions, but we also have the water molecule that's polar, and we can see that we have ion dipole forces. Okay, so it's incredibly important for you to memorize what is required for each one of our intermolecular forces to actually form. So, just a little recap of what you did in grade 10. So the intermolecular forces affect properties such as phases, melting point and boiling point. What's also very, very important is that we understand the kinetic molecular theory, because we're going to use it to explain a lot of these changes. So we need to remember that for a solid, particles are packed closely together and they're packed in straight lines and very close to each other, and that a solid has a definite shape and a definite volume. A liquid, the particles are still closely packed, but they're able to flow over each other. They're able to glide over each other. It has an indefinite shape. In other words, it takes the shape of the container it's in, but it still has a definite water. A liter of water is a liter of water. Gases are very, very far apart from each other, and they shoot about and move freely at high velocities and so on. They have an indefinite shape and an indefinite volume, meaning they take the shape and the volume of the container. You can take a liter of gas and compress it into a 200 milliliter gas canister. So they will always then take the shape of their container and also take the volume of the container that they're in. Okay. Now, this is an experiment that we would have done. So I'm just going to go through this. I'm going to see if I can't find a little video for you that explains these ones. Okay, so the first point that they make then, number one there. Substances with weaker intermolecular forces evaporate faster than substances with stronger intermolecular forces. Now these are literally a set of rules. So when we start comparing them and when we start doing the exam questions later on, we are actually going to be using these as our reasoning at the end. So we're going to say, yes, this molecule evaporates faster, and then the reason, because it has weaker intermolecular forces, and we state the rule. So you have to remember from grade 10 that you learned from the kinetic molecular theory that some molecules are bonded stronger together, and that's why they have a higher melting and boiling point, and they need more energy to actually break apart. Now that is these intermolecular forces. So for instance, something with induced dipole forces is a lot weaker than hydrogen bonds. So if we compare something like acetone to something like water, acetone will evaporate a lot faster because it's got weaker intermolecular forces compared to water. Then our second point there, substances with stronger intermolecular forces generally have a higher surface tension than substances with weak intermolecular forces. If you've ever filled up a glass of water, you would have noticed that while you're talking and not paying attention, that the water can actually almost stand higher in the middle than on the sides. That's because of the surface tension. In other words, the cohesion forces keeping the water molecules together. Okay, even if you just have a normal filled glass of water, just half full, you will see that the water molecules keep themselves together, and that's why we have water molecules that form drops and so on. So the stronger the intermolecular forces, the higher the surface tension. Then number 3, substances will dissolve in solvents that have similar intermolecular forces, or in solvents where the ionic bonds can be disrupted by the formation of ion dipole forces. So it's very, very easy. Like dissolves in like. Okay, so polar will dissolve in polar, non-polar will dissolve in non-polar, and ions will dissolve in polar solutions. Okay, it's one of the reasons why water is such an incredible universal solvent. Number 4 then. Substances with strong intermolecular forces will have a higher boiling point than substances with weak intermolecular forces, which makes sense. Hydrogen bonding, which is the strongest type of intermolecular force we get, and water has hydrogen bonding, means that water has a boiling point of 100 degrees Celsius. If we compare that to other molecules, they boil at a much lower temperature, because remember, from grade 10, when we're dealing with phase changes and we take a look at our temperature time graph, we have to increase the temperature before we get to that plateau where a solid becomes a liquid, and then if we increase the temperature more, we get to our next plateau where we get the change of a liquid to a gas. And water needs to absorb a massive amount of energy before that happens. Number 5 then. Substances with stronger intermolecular force travel further up a narrow tube. Now this is what we call the capillarity effect. This is got to do with two types of forces: cohesion and adhesion forces. Cohesion forces is the forces trying to keep the actual liquid together, which would be, in the case of water, the hydrogen bonding. Adhesion forces is the forces between the liquid and the sides of the tube that they're in. So for instance, if you've ever sat at the spur with your family and you have your straw in your cool drink, you'll see that the liquid in your straw is higher than the liquid in your glass. The reason for that is because the adhesion force between the plastic straw and the liquid is trying to bond to each other, so therefore it's being pulled up in the straw. But then the cohesion force between the water molecules or the cool drink molecules, they want to stay together, so they stick to each other and therefore they draw themselves up that straw. The intermolecular forces, microscopic properties, affect the macroscopic behavior of the substance. Now that's a mouthful. Basically all they're saying is the way that the molecules bond affect how the molecules act in terms of all these properties that we can see. Microscopic properties is properties we can't see. It's got to do with structure, electronegativity, polarity, all those things. Macroscopic properties is the properties we can see: boiling point, melting point, viscosity, density, capillarity, all these things that we described here. Okay, we will continue in the next lesson.